Hi everyone and welcome to Miss B Maths Teacher channel and thank you for watching. Today I'm gonna talk about optimization, which is pretty much the process of finding the maximum or minimum value of a function. And what does it mean in general is, for example, if you do own a business, you do want to maximize the profit, so you don't want to minimize the profit, so you're looking for variables that are affecting your business and the one that you can change so that you can increase your profit. Also in the same business you may look at how to minimize the cost of materials that has been used, so then your focus will be on minimizing the cost, so you don't want to maximize the cost. So pretty much it depends on the question, what are they asking you to optimize. So it could be either to minimize the cost and maximize the profit. So there are a few steps that we're going to follow in solving the problem. So it's handy to draw a graph if graph hasn't been given, and try to label if you have any information given, so to put on the graph. And then the next step would be to construct a formula, with a variable that you do want to optimize, and make that variable as a subject of an equation. So also we should write down the main restrictions if there are any for x variables. So the next step would be to find the first derivative and find the values of x which make the first derivative equal to 0. Now that we have found those values, that's right, you can have more than one. So the next step, it would be for every single stationary point either to use sign diagram or second derivative or the graphical test to actually decide or to determine if you have local minimum or maximum. By just doing step 3, we don't have enough information. So we do know the first derivative is equal to 0, but we don't know if we have maximum or minimum. The next step is to identify the optimal solutions, and then the last step, it would be to write your answer in a sentence. So pretty much you're answering the question. So now let's have a look at the question. I'm going to move this away, so I'm just going to minimize here in the corner. If we need to refer to that, we may just make it bigger. So the first step for this question, let's first have a look what the question is. So we do have 60 meters of fencing is used to build a rectangular enclosure along an existing fence. So there's an existing fence here, and 60 meters of fencing is used to build a rectangular enclosure. Okay, so now suppose the sides are adjacent to the existing fence x meters long. So this side is x meters long, and this side here is x meters long. So we have been asked to show that the area A of the enclosure is given by this equation. So, and we have been asked to find a dimension which maximize the area of the enclosure, so that actually these 60 meters of fencing it will be used as an optimal solution. So we do have graph, this one here. So let's see what else we can do here. That's 60, so that's x. Then we have 60 meters of fencing is given, so that can be used along those sides. We can see this is x and this is x as well, so these lines on both sides, it means the same length, and 60 meters is given. Now 60 meters are going to be used for this side, and this side. So pretty much it does look like we're talking about perimeter. So and then we do know that the perimeter is pretty much adding all sides. So if I put here perimeter of what we do have to enclose is pretty much x plus x and plus another unknown variable, which In this case, we're gonna call this one y. So that's gonna give us p parameter, okay, so it's 60 equal to 2x plus y. So looking at this one here, so we can see 60 and 2x's and, you know, plus y. And then we're trying to construct the formula in terms of x. So to making, you know, the x either subject of the sentence, so of the equation, pretty much we want to make everything in one variable. So as we can look here, they're asking us for this area to, you know, and we can see we don't have any y's in this equation. So it would be wise to actually here write y in terms of x's. So it's 60 and take away 2x. So these 2x have been moved to other side. So we have here y is equal to that. Now, let's have a look at part A. Show that the area A of the enclosure is given by this. So we do know that the area is equal to length times width. So, area is equal, length in this case is the value of y. So it is 60, take away 2x, and then times width is represented by x. So, and we can see that, you know, has been shown is, you know, exactly the same or similar. So what we can do, so therefore, if you really want to have in the same form, just rearrange x in front, so it doesn't make any difference. We can do that in multiplication and add the units. So this part has been shown. So that would be our step 2. So I can say that's step 2. Now looking here, it's step 3. So step 3 is asking us to find the first derivative. So, and find the values of x, which makes the first derivative equal to 0. So now the next step, so I'm just gonna put here next. So next. So a of find the first derivative. So what I'm gonna do here, you can differentiate this equation by, you know, using the product rule, or what I'm gonna do, I'm actually gonna expand this. So x times 60 is 60x, take away x times negative 3x is negative 3x to the power of 2. Now in order to find derivative of this equation, so dA to dx in respect of x is equal to x is equal to, what did you say? Yep, it's equal to 60. And then take away 2 times 2. So you remember this 2 here. It's going to come in front. So 2. So that it's going to give us 2. This 2 times 2 is going to be 4. So it's going to be 4x. So, and when is this equal to 0? So when 60 is equal to 4x, and when x is equal to 15 meters. So I haven't mentioned before, which is important here, we have to say that x has to be bigger than 0. Okay, has to be bigger than 0. Otherwise, we wouldn't have any length for x. So that was step 3. So we do have the values of x, which makes the first derivative equal to 0. Now, the next step would be for each stationary point, and we only have one. So we can use sign diagram or second derivative or the graph. So I'm going to use a sign diagram. So, and to see if you do have minimum and maximum when x is equal to 15. I'm going to do that on the previous page. Y is equal 60, take away 2x. So I didn't remember that. As you can see, I have copied here the steps as well if we do need to refer to them. So they're just here. So we have all these steps. And now we're doing step 4, isn't it? Yes, so we are looking for, we can either use a sign diagram, second derivative, or the graph. So what are we going to do today? We're going to use sign diagram test for the first derivative. So how are we going to do that? Sign diagram, line like this, and this is for dA dx. So first derivative is equal to 0 when x is equal to 15. So what we have to do now, or to find out, is what is the sign of the first derivative or the slope before the value when x is equal to 15, and what is the sign of first derivative or of the slope after 15. So how are we going to do that? So pretty much, let me just copy this or write down. So I think it's equal 60 take away 4x. So this is the first derivative. Okay, so how are we going to find those signs before and after? It's pretty much we're going to choose some values of x before 15, which is let's say 14. So it's less than 15. X is equal to 14. So and dA in respect to x is equal to 60 take away 4 times, instead of x we're gonna have 14. So and that is gonna be, let's go here, so it's gonna be equal to, oopsies, 60 take away 56. You can check if that one is correct, and it's equal to 4, and 4 is bigger than 0, so which means it is positive. So it is positive here. Now we do know if we have linear factors that signs are gonna alternate. What does it mean? Pretty much it means that we're gonna have negative here, but let's make sure that we actually have correct sign. So we're gonna choose number that's bigger than 50. So I'm gonna move this on the side. I'm gonna use x is equal to 16. So dA dx when x is 16 is equal to 4 times 16, 60. And at this stage, you don't even have to, calculate. So pretty much you're just looking, for the sign. And number here is negative, so therefore we're going to have negative. Now, this sign diagram is telling us that the slope is positive, so it's going up, and then after hit 15, it's going down. So, and then we do know when you have shape like this, that you do have the maximum. So, now, therefore, step 5 now. So, step 5 now is to identify the optimal solution. So optimal solution, maximize. So to maximize is when x is equal to 15, we still need to find the values of y. So, and if you do remember from y is equal 60 take away x to x, and we're gonna replace the x's with 15. So, and it's equal to 60 take away 30 is 30. And they're all in meters. So, the area is maximized when x is equal to 15 and y is equal to 30 meters. The last step is to write your answer in a sentence. So, therefore, you may say, sort of like this. The largest area here, area of the enclosure, is it enclosure? Okay, let's closure. Oopsies. Okay, let's get rid of that. Okay, the largest area of the enclosure closure will be maximized, okay, will be maximized when x is equal to 15 meters and y is equal to 30 meters. So I hope you have enjoyed watching this, and it did help you, and thank you for watching, and see you soon. Bye.